All right, let's talk about the multiplication rule. I mentioned this briefly and pieces of it when I discussed the opening question that you had on snow days within this particular module. So we talked about independent and dependent events a little bit in that video, and I talked about some of this sequencing. In other words, the snow days occurred in sequence. However, the probability remained the same throughout. Therefore, they were independent events of each other. One did not affect the other in that scenario of snow. Today, I'm going to use a deck of cards, and I'm going to work through some of these problems using the multiplication rule, and specifically working through problems using a deck of cards. I think I'll just limit it to that in this video. So the multiplication rule looks like this. It's the probability of event A and event B occurring, and that equals the probability of A times the probability of B, given that A has already occurred. So that vertical line right there just means given. So the probability of A times the probability of B, given that A has already occurred. Now, the first thing you have to figure out when you're working these types of problems is, are these two events that are happening in sequence, are they dependent on each other, or are they independent events? When we did the snow days across, or the probability of snow across 3 days, as just stated, they were independent events because they had the same probability across all 3 days, and the probability of snow on Tuesday was not affected by whether it snowed or not on Monday. If your two events are independent, then what you end up having is the probability of event B, given that A already occurred, is just the probability of B. And let's look at an example. Before we get to that example, let's talk about a deck of cards real quick. There are 52 cards in a standard deck of cards. There are 4 suits in a standard deck of cards: hearts, diamonds, spades, and clubs. And there are 13 cards per suit. Hence, 13 times 4 is 52. 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king, and ace. Those are your cards within each of the suits in a standard deck of cards. All right. I wanted to walk through this. I think I was just tooling around with it earlier, left it up there. Let's talk about this. We have a problem. We're going to select 2 cards from a standard deck, and we're going to use no replacement. In other words, we're going to choose 1 card, throw it to the side, then choose the second card from a standard deck of 52 cards. And the question that I'm asking is, given this scenario where I choose a card, throw it out, then choose another card, what's the probability that I'll get a king and a queen across this sequence? Well, the probability of getting a king, we're just drawing the first card. When we're drawing the first card, we have 52 out there, and there are 4 kings in a standard deck of cards. Then we're going to multiply that times the probability that we draw a queen, given that we've already drawn a king. Well, remember, we've already drawn a king, and we threw that card out, which means that logically we are left now with 51 cards, and there are 4 queens left because that first card we drew out was a king. We simply multiply across these, and that gives us 16 over 52 times 51, 2652, I think. And when you break that down, you get about 0.006. Not a very high probability at all, considering that probabilities always fall between 0 and 1 inclusive. So the 0.006 is definitely closer to that 0. All right, there's one example. That was an example with no replacement that made that second term, the probability of drawing a queen, given that we have already drawn a king, dependent. Let's look at an example where we replace. So I wrote replacement down at the bottom of this one. So same scenario. We've got 52 cards in front of us. We're going to draw 2 cards. What's the probability that we draw a heart and then draw a 6? Well, in this case, we're using replacement. In other words, we draw that first card, we look at it, it's a heart, we put it back in, and then we draw the second card. Okay? Let's map that out mathematically. Probability of drawing a heart. Well, the probability of drawing a heart, there are 52 cards, and there are 13 cards in every suit, 13 hearts, times the probability of drawing a 6 given that a heart was already drawn. Well, remember, this is with replacement. Probably should have used... Yeah. This is with replacement. So we're putting that card back in the deck, and we're drawing. Well, if we're putting the card back in the deck, we've now got 52 cards. And how many 6s are in the deck? There's 4. All right. So 13 times 4... 52, and 52 squared. It's 2704, I think. Yep. So when I take 52 and divide by 2704, I get about, it's about 0.02, so it's 0.019. Again, probabilities always fall between 0 and 1 inclusive. Infinite amount of numbers between 0 and 1 on the number line. And it can be any number in between those two numbers, including 0 and 1. In this case, 0.019 is also very close to 0. Not a very good chance that you're going to draw a heart, replace it, and then draw a 6. Okay. Those were the couple of examples that I wanted to give you tonight. I'm just going to start with that. I'll try to put another video up tomorrow with a few additional examples. And I'm going to assign a few problems out of iExcel this week and see if we can get started on some problem sets and lead into an assessment hopefully by the end of this week. All right, that's all I've got for you tonight. Thanks for watching. Appreciate it.